Now let's look at the intensity of the light. If the intensity of the incoming light is I0, remember I0 is proportional to E0 squared. After passing through the polarizer, the amplitude squared is E0 squared cos squared phi. So the intensity that comes through is I0 cos squared phi. I'll write that down. This is the polarizer. It has an axis. Incoming light has a direction of polarization. The angle between the two is phi. If the incoming intensity is I0, what comes out is I0 cos squared phi. Why is it cos squared phi? Because the electric field amplitude is E0. The polarization axis makes an angle phi with it. So what comes through has an amplitude E0 cos phi. Intensity is proportional to square of the amplitude. So incoming intensity is proportional to E0 squared. What's coming out, the intensity is proportional to E0 squared cos squared phi. Right? If I multiply both sides by proportionality constant, E0 squared multiplied by k gives me I0. E0 squared cos squared phi multiplied by k gives me outgoing intensity. This outgoing intensity is I0 cos squared phi. So what is phi? The angle between the direction of incoming polarization of the light and the axis of the polarizer. If the axis of the polarizer is placed exactly perpendicular to the direction of polarization of the light, nothing comes through. It's completely opaque. If the axis of polarization is the same direction as the incoming light's polarization, all of it comes through. Supposing you have unpolarized light. Unpolarized light, remember the direction of polarization is rapidly fluctuating. That means the angle between the direction of polarization and the axis of the polarizer, that's rapidly fluctuating. So in cos squared phi, phi is rapidly fluctuating. Again, let me be very clear about this. What comes through, what was the wave that I wrote down? Was E0 k cap, again cos ky minus omega t plus phi. So k did not change, omega did not change, frequency does not change, wavelength does not change when it goes through the polarizer. Only thing that changes is the amplitude and the direction of polarization. The direction of polarization becomes the same as that of the axis of the polarizer. Now let's look at this one. What if it's unpolarized light? I have a polarizer. Unpolarized light, the direction of polarization keeps fluctuating, so the angle keeps fluctuating. So cos squared phi keeps fluctuating rapidly between 0 and 1. The average value of cos squared phi is half. What you will see is not rapidly fluctuating intensity, because the fluctuating intensity fluctuates so rapidly that you can't see it. What you will see is lowered intensity by factor half. So you will see intensity I0 by 2. Let's make sure we understand what is the meaning of average of cos squared phi. Supposing you have a function f of x as a function of x, some function. As you can see, between x equal to a and x equal to b, the value of the function changes. If I were to ask the question, what is the average value of f of x over this range? The answer is, average, we'll write it as a bar, is integral f of x dx from a to b divided by b minus a. Okay, it's very important to understand this. If I wanted the average height of the students in this class, I would simply add all the heights and divide by the total number of students. So I get the sum of all the heights, sum S divided by number of students n, that's going to give me the average height. Now average height has the following property: if all of you had the same height as the average value, then the sum would be the same. Is that okay? Let me repeat that. All of you have different heights. I sum all the heights and divide by the number, I get the average height. But just imagine for a second that all of you had the same height. What would that be? That would be the average height. Alternately, if I take n and multiply it by the average height, I get the same sum. Let's go to a function. Sum is like an integral. Integral f of x dx is nothing but the area under the graph. The area under the graph divided by the width is the average height. What does it mean? It means the following: the function goes from this value, goes up, comes down, goes up there, right? Supposing the average value is that. Consider this rectangle. What's the area of that rectangle? B minus A times the average value is equal to the area under the curve. So the average value is that height, such that if the function were just constant, the area would be the same. That is, if all of you had the same height, then the sum would be the same. It's an analogy for that. So instead of summing, if it's a continuous variable, what do? You integrate. If you don't understand all that, you can simply take it as a definition. Now if I have a sine function or a cosine function, let's take a sine function. Over one time period or one wavelength, the average value is 0. Equally positive as negative, or a better way of looking at it is this area is the same as this in magnitude, but they have opposite signs. So the sum is 0. So the area divided by b minus a is 0. So the average value of sine or a cosine is 0. The average value of a sine squared function, if I square this, it's going to look, remember sine maximum value is 1, sine squared also is 1. So sine, but it will have a slightly different shape. Sine will be, again, both sides will be positive. Negative side also will be positive. Now you can see the area is not 0. How do you prove that the average value of sine squared over one wavelength is half? You have no choice but to integrate. But I'll tell you a shortcut. Watch this. This is a sine function. And in blue, I'm going to draw the cosine function. Minimum, right? Now if I square the two functions, the cosine function is going to be something like that. And if I square the sine function, it's going to be like that. Convince yourself the area under the cosine squared function is the same as the area under the sine squared function. This half is going to be that half. This half is going to be that half of the hump. You can convince yourself the area under the cos squared function is the same as the area under the sine squared function. But sine squared theta plus cos squared theta is 1. Integral of sine squared x plus cos squared x dx is equal to 1. From 0 to 2 pi, 1 dx is going to be 2 pi. 2 pi. What should I do to find the average? I have to divide by 2 pi. B by, say, when I divide, the answer is 1. That's what I was saying, sorry. So the average of sine squared plus cos squared is 1. But sine squared and cos squared have the same average, so each one is half.